So anytime we fit a least squares regression model in CodeApp, it gives us this R squared value. What does R squared mean? So one way to think about it is that it is just the correlation squared, right? Remember, correlation measures how far the points fall from the line, and you can square that value to get R squared. But there's another way to think about it that has to do with the residuals. So let's start by getting rid of square footage. Let's think about if we did nothing at all, if we just looked at the prices, how much do those prices vary, right? So obviously we've got a lot of variability in this data set. And if we had to predict price and we didn't have another variable, basically we would have no choice except just to go with the mean, right? We would just have to guess the mean every time, and sometimes we would be too high and sometimes we would be too low, right? And so if we look at the standard deviation here, this is telling us how much the points vary around the mean, or in other words, if we were to just guess the mean price every time, how far off would our predictions of house price be? In other words, how large would our residuals be if we just used the mean and we didn't have any predictor? But let's compare that to what the residuals would look like when we did use square footage. So remember, these residuals that are in the table, we calculated those based on the least squares regression line. So I'm going to make a similar graph here. I'm putting the residuals on the y-axis. So they're centered there around 0. The mean of the residuals will always be 0. And I'm going to look at the spread here. So I've got the standard deviation. We can't immediately compare them because the scales have changed, but we can look and see what these values are. So 240,000 basically if you just use the mean, no predictor. Whereas when you use square footage as a predictor, it's smaller, right? The residuals are smaller. But how much smaller? How much have our prediction errors gone down? So we can think of this like a ratio. So on the bottom, we're going to put how much unexplained variation we have if we don't use any predictor at all. So this is the standard deviation from the model with no predictor, right? So this would be the amount of variability that's unexplained variation with no predictor, right? Where we're just guessing the mean every time and that's it. And we're going to compare that to the model down here. So we're taking the standard deviation, 177,194. This is the unexplained variation with square footage as a predictor. Unexplained variation with square feet as predictor. And actually the R squared isn't based on the standard deviation. It's based on a related measure called the variance. The variance is just the standard deviation squared. So we're going to square each of those numbers. Okay, so if we do that fraction, we get 0.54. So what that tells us is that our unexplained variation, put that in quotes, unexplained variation is about half what it was before. Right? We've cut down the unexplained variation, cut down the prediction errors by about half. So this is talking about unexplained variation, but R squared is defined in terms of explained variation. So we do 1 minus this value, 0.54, and we get 0.46. I will say that this is a slightly simplified version of the formula, but this is the basic idea, right? So what this number is telling you, this is R squared, this is telling you how much variation has been explained. Okay, so to interpret that 0.46 number that we see, we would say that 46% of the variation in prices has been explained. Right? R squared measures the explained variability, has been explained by the model using size. And in general, that's how we interpret R squared. We say that blank percent of the variation in Y, whatever our Y variable is, has been explained by the model using X.